Okay, sorry, which one was that? S, which one? 17? Okay, number 17. Okay, can you guys be quiet so I can start working on this? Okay, 17 and 19, right, S? Okay, you better be paying attention then, okay? Stop texting there. Okay, so you're asked to find differentials, is that right? Find the differential dy of the given function. Okay. So looking at 17, you're going to differentiate the left, you get a dy. Right? When you differentiate y, you get a dy. And on the right hand side, if you differentiate x, what do you get? 2 and derivative of cotangent squared x. So first of all, you're going to get a 2, right? Then you're going to get a cotangent x, and then the derivative of cotangent x. So it's secant squared, cosecant squared, negative cosecant squared. So then this guy becomes a plus, okay? And this guy becomes CS c squared x dx.
Can you explain how to do the whole cotangent squared x and like cotangent?
Okay, so you're going to use the chain rule for this, okay? You're going to use the chain rule for this. So pretend that this is like an x squared function. Pretend it's like an x squared function. So when you differentiate this, okay, so if it was an x squared function, the 2 comes down, and then it would become x, right?
Yeah.
Except that instead of x, it's cotangent x. And then using the chain rule, the derivative of cotangent x. Okay. So, okay, let's go back and do d by dx of cotangent 2x. Okay. So now, this one here, there are really two functions. Okay. There's an x squared function and there's a cotangent function. Okay. This one here, there's only one function. It's just cotangent. Okay. So derivative of cotangent is negative CSC squared 2x times the derivative of the inside, which is the derivative of that. What's the derivative of 2x? 2. Okay, so you're really using chain rule in different forms. Sorry, yes, can you ask me the question?
The cotangent squared x is basically saying x squared times cotangent.
Oh, wait a minute.
Cotangent x times cotangent.
Yeah. Derivative. Hang on, Henry. Can I finish this, please? Derivative of cotangent is cosecant squared, right? Yeah. So I got that. Okay. Yeah. Henry, you have a question?
So basically, all one we can just use power rule.
You could, but it's going to be longer.
Yeah.
You could. Yeah. Yeah. What is what? The derivative of 2x. What's the derivative of the inside? It's the derivative of 2x. 2. Right? You guys are, you go to, I hope you guys are studying, okay? You got a freaking final next Wednesday. Okay, you're asking me some fairly basic questions. It worries me. Okay. Yeah, no, there's a lot of stuff in this. Okay, you may do 19. Yes, I'm asking you, do you want me to do 19? Sorry? Oh, really? Let's do it then. So number 19. So you're going to go dy. Can you guys pay attention here so that I can teach? Okay, I'm trying to fight. I'm competing against your voices here. Okay. Dy is going to be equal to 1/3. What's the derivative of cosine?
Negative sign.
Negative sign. So you're going to write out straight out negative sign 6 pi x minus 1 over 2 times the derivative of the inside, which is the derivative of this guy. Sorry? 3 pi's. Everybody with Janice on that. Everybody with Janice on this?
Yes.
No? If you rewrite 6 pi x minus 1 over 2 as 3 pi x minus a half, is it easier to see it that way? Okay, the derivative of 3 pi x minus a half is 3 pi. Yeah? So then this 3 and this 3 cancels, and you get minus pi sine 6 pi. Janice, what's the answer at the back? Oh. Well, we missed 17 now. Okay, you guys all right with this stuff? Okay? All right, moving on to the last topic then on chapter 3. And today is actually word problems, okay? We're going to do a bunch of word problems. So take this down and then let me explain what this is all about, okay? So what this problem is kind of explaining, trying to do is, you want to estimate the error in something, okay? Like in this particular example, you want to estimate the error in the volume of a sphere, okay? So when you're making a sphere, you know that you're not going to get a perfect sphere. You're not going to get, at least in the sense that the radius will be not exactly what you want, okay? Well, you can always measure the radius of a sphere by getting a caliper, putting it at the ends, and finding the diameter, and you get the radius out of there, okay? So that way you can measure the error you've made in the radius. But that error in the radius is going to result in an error in the volume of the sphere, right? Because the volume of the sphere depends on the radius. Now, it's really hard to measure the error in the volume. What are you going to do? Cut the sphere open, put some water in it, measure it and all that? Or you've destroyed your sphere, okay? So can't quite do that. Instead, what we do is we use calculus and differentials to estimate the error that we made in the volume as a result of the error in the radius. So here's the actual example, okay? And so here's the numbers on it. So get this down, and then I'll go over it. Sorry? Nice. 4 over 3 pi r cubed. Good job. If you read this sentence here, or the paragraph here, or whatever, the couple of sentences, can you infer what dr is? Can you infer? Remember, dr is going to be the change in the radius. Can you infer what it is from that sentence there, or those couple of sentences? Sorry? Thank you. Plus or minus? Right? And if I do a differential of this, I get a dv on the left. What do I get on the right? I'm going to differentiate with respect to r, okay? dr. Okay, remember that when you've got differentials, you've got two variables there, okay? You're going to have a dx, dy, or you're going to have a dv, dr, or dA, dx. You're going to have two variables, okay? Two differentials, always. Okay? And so then this guy becomes 4 pi r squared dr. Remember, dv is going to be the change in the volume, or the error in the volume, whatever terminology you want to use, okay? So we're going to go 4 pi. What is the nominal radius? What is the theoretical radius that I want the sphere to be? Sorry? No. The radius, not the error, the actual radius. Oh, sorry. Yeah, my bad. What did you say? 0.7. Thank you. I was thinking of another problem. And what's dr? So I'm going to put my plus or minus here. Okay? Can you plug on your calculator and give me an answer to this stuff? Chug this on your calculator. Sorry, what you get?
0.615.
Okay, 0.06.
0.0615.
Okay, 4 places.
Yeah.
0616.
Yeah.
Not 4 sig, 4 decimal places.
Yeah.
Yeah. Units. It's volume, so inches cubed. Okay. Now, getting a number like this doesn't give you a very good feel for the magnitude of the error. Okay. So, an alternative way of measuring the error would be relative percentage error. So when you say that something is a percent of something else, it gives you a better feel for how big the error is, how small the error is. Okay? So the way you do this is you take the error you made, which is going to be 0.0616 da 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 da. Okay? That will be your stored value. Okay? Or alternatively, you can just use this symbolically. Okay, let's do that. Okay, let's use this symbolically instead of having to do with numbers. So you will take 4 pi r squared dr, and you're going to divide it by the theoretical volume of the sphere, which is 4 over 3 pi r cubed. Okay, and you're going to kind of simplify this. So the 4's cancel, the pi's cancel, the r goes to the top, and it leaves, sorry, the 3 goes to the top. One of the r stays downstairs, times dr, times 100, okay? Because you want to write it as a percent. You want to write it as a percent. So then this is going to be 3 times dr, we agreed was 0.01. R we agreed was 0.7 times 100 plus or minus, and then this gives you a number. Can you guys chug on that and give me a number? So that's 3 times 0.01 times 100 over 0.7. 4.2857%. Okay, don't forget the percent sign there. Okay, so this gives you a better feeling. Okay, the error is like 4%. Okay, gives you a better feel than just a number 0.0616. Okay, so do you guys get how to do differentials and do error? Yes. Because of whatever we did in building the sphere, we made an error of 0.01 inches in the radius. As a result, the error in the volume is about 4%. Okay? That is the physical error in the volume, the dimensional error in the volume. In other words, if the volume was supposed to be 10 cubic inches, it's going to be 9.9484 cubic inches. That's what it means. Percent error is just giving you a relative feel, right? I mean, right? Okay. So if you've understood this, I want you to practice number 28 or do the work on number 28. Okay, and then I have one more example to do and then we'll be done. Okay. This down, please. This should not be new, okay? It's just a rehash of things, and I'm just giving you more terminology. In other words, differentials are of the form dy equals y prime. This is crucial here, okay? This understanding here. Okay, shh, shh, shh. This understanding is crucial here, okay? This comes from this here, okay? So y prime is equal to dy by dx. And if you treat dy by dx as a